Okay, so first of all, thank you to the organizer for the invitation. It's very nice, of course, to meet finally in person after 1 year and a half of COVID crisis. But yeah, I gave this very broad title, Deciphering Mental Dynamics using global seismic imaging, but that's maybe too ambitious, but maybe we can rephrase it as how can global seismic tomography be understood with thanks to geodynamic modeling. So, yeah, as you all know now since this morning, the seismic waves are a very powerful tool to investigate the interior of the Earth, and we use them to map seismic velocities anomalies in the mantle. And so this is because we observe some anomalous travel time compared to a reference model, and so we can use this delay time to map the 3D anomalies. And then you end up with this kind of tomographic model that you are now used to see. And I just wanted actually here to emphasize the motivation of doing this is that we get, of course, the seismic velocities, shear wave or P wave velocities, but they are actually dependent on temperature, pressure, composition, presence of melt. And that's actually what we want to better understand, to better understand what is the thermal or compositional state of these heterogeneities that we see with seismic tomography, to better understand the geodynamic. So we all know these very famous images from tomography, where you have a slab sinking into the mantle. Actually, I should say fast velocities anomalies, but they are correlated with some earthquakes, deep earthquake location and slab and subduction zone. So we interpret this as a cold slab sinking into the mantle. We also have these images of slow velocity anomalies rising from the CMP up to the surface. And all of these images, of course, they shaped our interpretation of what is the dynamic of the mantle. And so that's definitely the debate after these images. So I won't go into the details of the method. Christophe already gave you a nice overview. But basically, we have data, and we want to inverse for the model. And as Christophe already and Stefan already said, we have to make choices when we do this inversion. So, of course, I would still say the main ingredients are the seismic data that you want to use, and we try to combine a maximum of data, so normal mode, surface wave, body waves. But then you also have other choices to make when you do this tomographic inversion. You have to parameterize your model to choose for a theory, and you have this damping parameter. And so, of course, when you look at a tomographic model, you have to take into account all of these choices before making any interpretation. So I will show you some, so we made tomographic models, and I will show you some results of this. So we wanted to combine different seismic data, so surface wave, normal mode, and body waves. So the idea behind is that you have several data sets that have different frequency content and also different depth sensitivity. So when you combine all of them, you maximize basically your coverage and your depth sensitivity. So I will just describe a little bit more the data that we used. So we use some phase velocity of surface waves, relay surface waves here, that we get from an automated waveform inversion that has been developed by Eric de Bail. So for a given pair of earthquake and station, what you invert for the path average, attenuation or quality factor, and velocity profile. And from this, you get actually the phase velocity. And if you do this job for a massive data set, you can build these phase velocity maps, which gives you the phase velocity perturbation of this mode due to the presence of lateral heterogeneities into the mantle. So, for instance, this mode is, you have the sensitivity kernel. So you see it's sensitive to the uppermost part of the upper mantle. So that's why you see the correlation with the surface tectonic, the ocean ridges, and the cratons. So we've done that for several periods, 60 periods, and considering the fundamental mode and up to the fifth oversum. Then we combine that with also normal modes, so these modes that are the vibration modes of the Earth as a whole when you have very big earthquake. And here, basically, you observe then when you do a Fourier transform of a very long recording of an earthquake. Here is an example for the Sumatra earthquake. So if the Earth were spherically symmetric, you would have this red spectra with this unique peak for each normal mode, and quite narrow. But if you look at the observed one, which is the black curve, you can see it's more complex. What you see is that actually you have several peaks for one mode, or two modes for a unique peak. And that's what we call the splitting and the coupling of normal modes. And these are due to rotation, ellipticity of the Earth, and also the presence of 3D heterogeneities into the mantle, into the Earth actually. So just to repeat again, so you have this observed spectra, the black one. If you would have a spherically symmetric Earth, you would have a unique peak, but then you include the ellipticity and rotation, you have the dash blue line. And then if you add the effect of 3D heterogeneities, you can fit the observed spectrum. So then one way to look at you can measure this effect of 3D heterogeneities, and we plot that as a splitting function. So this map gives you the frequency perturbation of this mode at every location due to the presence of 3D heterogeneity. So we have corrected for ellipticity, ellipticity and rotation effect have been corrected for. And here you have the sensitivity kernel for this specific mode. So we haven't made a measurement by ourselves, but there are some published measurements of the splitting and coupling of normal modes. So we compiled some published data, and so they are done they are related to the spherical harmonics degree. So we use them only up to the degree 8, and this is the total number of data we found in the literature. The only limitation from this data set is that it's only sensitive to even degree, the even spherical harmonic degrees. So that's why we also combine them with cross-coupling coefficients. So you actually do the same job, but now you are measuring the coupling between two modes, and you also can build a splitting function. There are much less observation measurements. However, they are important because they can constrain both even and odd degrees. And finally, we combine that with body wave travel time, measured actually by Christophe, which here include S, SS, and SCS waves. You have here an idea of the coverage we have from surface to the CMB, and of the sensitivity that we have with this data. So that's a big part of the model, but as you know, we have to make other choices, the parametrization. So here is how what we decided. So we inverse only for VS, and we impose some a priori correlation factor between VS and density and VS and P velocity. We use spherical harmonics for the lateral parametrization and the spline function for the radial parametrization. And we did a first model, which is a long wavelength model, size globe 1, based on normal mode and surface waves. So it is developed up to degree 20 in the upper mantle when we have surface waves. But of course, in the lower mantle, it's only constrained by normal mode, so it's a very long wavelength, and you have only 8 degrees. So that's why you see the loss of resolution. But we see the imprint of tectonics in the upper mantle. You can see, of course, very smooth, but the subducting slabs in the mid-mantle and LLSVP at the base of the mantle. So large low shear velocity provinces, these slow velocities beneath Pacific and Africa. And that's where I wanted to zoom now. It's because we found that the pattern in size globe 1 for this LLSVP is a bit different than what is observed in other tomographic model. And we wanted to understand why. And so one way to look at that is to separate the odd and even degrees of the model, even and odd part of size globe 1. And here you have you go deeper down to the CMB, and you see that at 2,700 kilometer depth you have this very strong degree 2 and some odd degrees. And as you go deeper, you decrease the degree 2 and you increase some the odd part, and that's what makes this pattern more complex. And in our model, the odd degrees are only constrained by the coupling of normal modes, so this new pattern come from the new information we include in the model. Another way to look at that is look at the spectrum here at the 2,800 kilometer depth, and you see that so SP12 RTS is another model from Paula, and you see we agree with this decrease of degree 2, but in size globe 1 we have the cross-coupling, so we see stronger odd degrees in general. So now the question is, what does it mean, or does it mean something about Mantle dynamics? So there is this idea that the LLSVPs are shaped by the subducting slabs that reach the CMB. So then does it mean anything that if we have a stronger degree 3? And also this large long wavelength pattern of heterogeneity at the CMB controls the heat flux at the CMB, which has an impact on core dynamics, and even it has been shown that it can impact the inner core structure. So that's an open question. Should it be taken into account then in the dynamic modeling? So then we went for a new version of the model, including now the body wave dataset. So it's a size globe 2. This one is developed up to degree 40 in spherical harmonics. And so, of course, we see more details in the mantle structure. Still the ridges and cratons in the upper mantle, and some slab down to 1,000 kilometer depth, and the LLSVPs down to the CMB. And here, something that we looked at is what is happening in the mid-mantle around 1,000 kilometer depth, because the size globe 2 came in the context of several studies that published or reported observation of reflection in the mid-mantle observed from 660 down to 2,000 kilometer depth. And actually, these reflections are quite widespread in the mantle, and not always correlated with specific structure. So we were asking ourselves, is there anything that we can see in the tomographic model? Because we could, when we were plotting some cross-section, we could see the stagnation of some slabs at around this depth, or also the LLSVPs rising and stopping or spreading at around 1,000 kilometer depth. So we looked at the spectrum of size globe 2, and what was very clear. So here you have the harmonic degree, which means here you have shorter wavelengths and longer wavelengths. And what was clear is you have this depth range here from 660 down to 1,800 kilometer depth, where you have this accumulation somehow of shorter wavelengths heterogeneities. And you can quantify that by looking at the flatness of this spectrum, by fitting them with an exponent, a power law, and you can look at the exponent of this. And you see that, of course, size globe 2, the red curve is very flat in this depth range. But you can also see that other models have a kind of maximum of flatness also in their spectrum at around 1,000 kilometer depth. So now the question is, what does it mean in terms of dynamics? So we don't have the resolution to see a discontinuity. So if we see this whole range, it would mean that this discontinuity has a very large topographic variation. Or maybe it's just a transition zone, and because of some reason, you have an accumulation of small-scale heterogeneities. So the origin of that is still open and in discussion, but there was different studies that can provide some insight. So you have here this study reporting this viscosity jump at around 1,000 kilometer depth, and something interesting is that they provided this autocorrelation matrix from a thermal field after dynamic modeling, so including or not the viscosity jump at 1,000 kilometer depth. And what you see in this case is that you have this decorrelation level that we actually get also in size globe 2, so that's maybe a nice observation. And there are also some other modeling that reported that you could also preserve with time SiO2 enriched region, which are highly viscous, and that could also explain this transition in viscosity at around 1,000 kilometer depth. And in this kind of modeling, you would also expect very large topographic variations. Could it be a chemical layering? So I was actually surprised when you look at this geodynamic modeling, when you see how you can enrich the lower mantle with heterogeneities through the subducting slabs. So maybe you have this global chemical layering enriched in basalt because of the subducting and the convection. So that's all for this 1,000 kilometer depth change. And I think we still need to discuss and find an explanation for this observation. So I wanted to also talk about attenuation. So we only saw a velocity tomographic model, but as I told you, the aim is finally to discuss the thermal and compositional state of the Earth's mantle, and this is impossible if you have only this information about velocity. So we need to have another observation to really discriminate between the two. And one of these observations can be attenuation. So seismic attenuation is the fact that seismic waves lose energy as they propagate. It is related to the material properties. And we quantify that through this quality factor. So the higher is this quality factor, the lower is attenuation. But then when you have the two information, we can try to say something about the thermal or compositional origin of these anomalies. So that's what we have done in this more recent study. So again, we use this automated waveform inversion to produce attenuation and velocity model. So it's a waveform inversion. You have this path average quality factor and velocity profile, and you can do that on a massive data set, and you regionalize this profile, and then you get 3D variation in velocity and in quality factor. So it's only for the upper mantle here because we use only surface waves. And, but what is interesting is that then we get two models with exactly the same data set, the same procedure, so the same smoothing, horizontal and vertical. So they are self-consistent. And there are just some specific treatment for attenuation, some correction, but otherwise they are exactly, they have done with the same procedure. So what can we say about the Earth's mantle using these two information now? So we can look at take some experimental result that tells us the quality factor is related to temperature through this kind of relationship. So here you have the grain size. You have here it's if you want to include the water effect. You have here the period at which you are looking. And then you can put the parameter you need, and you can get the relationship between the quality factor and the temperature. And then you can go a bit further, and for the temperature, you can go back to the velocity now, using, for instance, perplex, and choosing some compositions, for instance, a paralytic mantle. And then you can have this curve here relating the attenuation to the velocity. Now, on this graph, you can put the data, and here our data are the tomographic model, the Q factor and the velocity model. So every dot here is a geographical location in our tomographic model. And what you see is that the curve does not explain all the data, and you have this large part here, which low velocity that you cannot explain with this thermodynamic relationship. So we need to find a way to lower the velocity, and this can be done by adding melt. So that's what we did. You can so we use some experimental data to work to have the effect of melt on velocities, and then you can lower the velocity with some proportion of melt. So the red color bar here goes up to 1%, and it's the proportion of melt. And you can look at the results in maps. So here you have the map of the proportion of melt with depth. So you see that we find actually that melt is widespread in the lithosphere and down to 300 kilometer depth. But then we actually also improve a little bit the attenuation, the inelastic model, and we use a temperature-dependent inelastic model. So this is based on work that on the fact that you have this pre-melting effect. So you have a large drop of the velocities when you come closer to the solidus. So you can take that effect into account, and then you obtain the blue curve here on the graph. So you have lower velocity, which means that you need less melt, and also which means that you are left with some regions that have fast velocities that you cannot explain with melt, obviously. And when you plot that as map at different depths, you see that the fast velocity regions are basically the cratons, and we find melt beneath ridges or the lithosphere, the oceanic lithosphere in general, down to 200 kilometer depth. So then last observation that we can make is to look at the percentage of melt with the plate velocity, and you can see that at different depths that you have a larger percentage of melt for fast-moving plates. And this actually reminds us another previous observation that was made by De Bell and Ricard, that you also have a greater crystal alignment for fast velocities, fast-moving plates. So the question is, does the melt facilitate deformation so that you have this alignment, or is it the inverse, so the deformation, does it favor the retention of melt, or is it a combination of two? And maybe that's a question that geodynamic modeling can answer. So these are the results I wanted to show, but I also wanted to talk about some perspective. And there is currently, so here is I mean, it's a more recent picture of some tomographic model, and I mean, we reached somehow a consensus for the long wavelengths. But there is something very interesting, is that there is an initiative for building a 3D reference model, which is currently done by Raj Moulik and collaborators. And so they are collecting data to build reference data sets so that we can build this kind of reference, 3D reference model. And the perspective for all the other work I've shown, so we are working on updating the models and also extending the attenuation model to the lower mantle by measuring the attenuation on body waves. This is under ongoing work. And I just wanted to finish on also new data that are available. So there is a new field, rotational seismology, that is developing. And I just wanted to advertise for the poster of Raphaël Abreu today, and who will show this preliminary observation. But we are seeing on this new data also body waves, and body waves sampling the deep mantle. So the question is, can this data help to better understand or better see the lower mantle? And I will stop here. Thank you.